Well, let me just quickly introduce our speakers. So in this occasion, we have a duo. And the reason we have the duo is because they belong to two spectrums of the math-X science. So we have Jacob Scott, who is a medical doctor, although he didn't have a very straight transition into medicine. And if you'd like to ask him about his career path, it's a very interesting career path, and it actually shows that you can reach to your goals by going to different directions. And he's currently the head of theory in the Transnational Hematology and Oncology Research Group and Department in the Cleveland Clinic, which is the top clinic in the country in the United States. And then here we have Philip. And he's an applied mathematician. And what they have been doing is that they're collaborating for a number of years, one wearing his hat as a medical doctor, the other one wearing his hat as a mathematician. And over the last couple of years, I have seen them speaking on a form of a dialogue on how to set up a collaboration. And they're going to do this exercise for us.
Okay. So thanks a lot for the introduction, and thanks for the opportunity to talk about our work. So I'm Philip from a mathematics background. I'm from Chalmers and the University of Gothenburg, not too far away. And this is my collaborator, Jake. I'll let him introduce himself.
Yeah, so I'm Jake. I'm a radiation oncologist, so I actually use the images you just saw all the time from the last talk to save lives, but only one day a week, and the rest of the time we try to use theoretical models to take care of cancer. But today we're going to pretend that I don't know anything about maths, which is close enough to the truth relative to the real McCoy, and we're going to play out a little bit of a dialogue that goes back and forth, and it highlights a few things. One, I'm going to ask some hard questions of Philip, and he'll ask some hard questions back, and I think it highlights the relationship he and I have had for many years, and also how a dialogue can form and start, and where maths can feed in to difficult topics. And so we are going to talk generally about some game theory, but also some other different types of models. And we'll highlight other people's work along the way and our own, but for the purpose of the dialogue, we'll just sort of pretend it's all within one conversation. And I'll start by presenting a clinical problem that we see all the time. And I think most people now have heard about personalized medicine. And this is really the last 10 years or so. Actually, it really started in the late 90s with the discovery of sort of cancers that were completely dependent on a specific mutation. And this really changed the way we thought about cancers, and it really gave us an idea that we could develop rational molecules that would stop single actions of proteins. And it really beautifully fit into our paradigm of the reductionist model of biology. There's one thing wrong, we fix the one thing, the problem goes away. And this is a sort of poster child example of that success and also of that failure. And as a clinician, this is something we see all the time, either in this form or others. This is just a striking visual form. And so what you're seeing here is a picture of a single gentleman who came in with a widely spread or metastatic melanoma, which is a kind of skin cancer that I'm sure you've heard of that comes in the form of moles that can then transform. But this can also spread to many parts of the body. And this image is striking because it's spread underneath the skin, so you can see it. Most of the time it appears, you can only see it using tomographic images or MRI and other places, so the person might look on the outside normal but might be filled. But this image shows us really a visual representation of how these cancers can spread and cause problems. But in this case, this gentleman was lucky in that his cancer was fueled or spurred on by this one special mutation. And it's got a big long name. It's called BRAF V600E. It simply defines a single point in the genome where something was messed up, and it fueled this growth. And we have a medicine for that, a pill called vemurafenib. Take the pill, not even any side effects. 15 weeks later, beautiful, normal, healthy-looking gentleman. And this is great. And this is the promise of personalized medicine. However, every single time this occurs, without fail, resistance to that single drug develops for a number of reasons, and the cancer roars back and takes the patient's life. There are some examples when this has become a cure, but the vast majority of these don't. And so, most of the time, what I'll do is re-biopsy the patient and look for yet another single targetable lesion. But there's something that's frustrating me, because I feel like this happens every time, and I often do find another mutation, but I feel like there's something else that must be going on. I just don't really know, what else to look for. And so I've been looking around talking to different friends, of course, biologists, because they'll know all the answers. But I wonder, I don't know, do you have any insight into this, Philip?
I mean, so this sounds like a complex problem, but I think that you can actually somehow tackle this with mathematics. So, in fact, in the last, say, 10 or 20 years, there's this new field that has grown out, and it's called mathematical oncology, and it's about modeling and describing tumors using mathematics. And although this field is rather new, it has traditions that go further back. So when people started doing experiments with tumors, they injected tumor cells that came from humans into mice, and they measured how these tumors grew over time. Then you would typically see growth curves like this. And when they did this, they thought of as the cancer cells as an invasive species. It's been injected into the body of the mouse, right? So it's not there to begin with. And it's growing, it's taking over. So it was sort of close at hand to start looking at tools that were around, and one of that was theoretical ecology, which has been around since the turn of the last century.
Philip, this is way too simple. All you're talking about here is a simple single growth of one type. And we really know that the genotype of these makes for many different types of species, not just one. This is sort of, I think it's nice that you can do this, but it's really a silly oversimplification.
No, so this is what people did in the 60s, say, and when those were the experimental techniques that were available. Now we know much more. Now we can take detailed images. We can also take samples from actual tumors and we can sequence them. And of course, the picture is now much more complex. So the way that people are thinking about tumors now is more like an actual ecosystem. So we have many types of tumor cells. They're interacting with normal cells, cells that form blood vessels, the supportive tissue, and so on. So you should think of this as some sort of web of interactions here, where the cancer cells interact with one another, but also with the healthy tissue. And there are tools from theoretical ecology to describe this.
Well, that's interesting as well. But I mean, really, when I sample a tumor, first of all, I don't see plankton or termites. I see other tumor cells. But really, I see a genetic readout that tells me about the differences between the individual tumors. And here, even if I can believe that you could model the tumor as a protozoan, for example, I don't see any of the heterogeneity within the tumor or the idea even of capturing that. Is there anything that you can think about, or in mathematics that could think about this heterogeneity?
Yeah, so I think here the other sort of strand of thought in mathematical ecology comes in, which is evolutionary theory. Because since the 70s, we know that tumors are evolving, they're constantly changing, and that this occurs through Darwinian evolution. And the mathematics for describing Darwinian evolution was developed in the 20s and 30s, known as the modern synthesis, when the Darwinian idea of selection was married with Mendelian hereditary. And for example, here is shown one tool that is used, which was developed by Sewell Wright, which is a fitness landscape. So we can hear, we're talking about resistance, right? So here, but maybe it's easier to think about bacterial resistance. So we have a bacterial species, and it's sensitive to 4 different types of drugs. So the zeros, this binary string here represents that it's sensitive, 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 sensitive to, say, drug A, B, C, and D. But this can then mutate and change, and this genotype here will be resistant to the first drug, but sensitive to the others, whereas this one is resistant to type B. And then we can list all possible combinations here of genotypes. And this is what is shown here. And then, because mutations are discrete, we can't just go from here to anywhere in this landscape. But we can only take discrete steps. So we can have one mutation that takes this genotype here into this one, which now is resistant, and so on. So this is how we can connect this up.
So you're saying you could connect these 2 ideas in some way?
Yes, because here you can assign, to each of these genotypes, you can assign a fitness, a growth rate, which will tell you how it will grow in certain conditions in the presence or absence of a drug.
Well, that's interesting. I was just thinking about some experiments I've done recently, I just happened to bring some images with me. But what we've done in this experiment is we've taken 2 different types of cells, and one type which we've labeled green in this picture, is quite sensitive, just like you said, to a certain drug. And the other type, red one, is very resistant to that drug, almost like you described in that funny picture you showed. But what we see is this sort of complex dynamic between them as they grow. So I'm not sure, I mean, I guess it could be as simple as, like you said, there's different growth rates, but I really do think that there's probably more going on. We can actually take data over time and count the number of cells during these experiments at different time periods. So you think we could pull out both the growth rates that are different? I mean, I could even probably guess at that, but we have this idea that there might be some sort of interaction happening, and I don't see any way that you've thought about that.
No, but there are ways of dealing with that as well. So we can think of different genotypes or cell types interacting with one another and growing at different rates because of the interaction. And here, this is methods that were developed in the 70s, known as evolutionary game theory, where different types compete against one another. And a good illustration of this is the rock, scissors, paper game. So imagine that we have a room full of people.
We do.
We do. Everyone is playing rock, say. When we play against one another, if we win, we keep on playing because it's a good strategy. But if we lose, we adopt the strategy that we lost against. Okay, so that's the dynamics that we set up. And into this room of rock players, we introduce a single paper player. Now, this paper player will start winning, and people will start adopting the strategy. We can illustrate this by looking at this simplex here, where on the edges here, so this is the situation with all paper players. We introduce a single scissors player into that, and we'll move along this. The dynamics will take us along a trajectory to this place here. We now introduce a single rock player, and we will move up here to where everyone plays rock, and so on. And we can move along here on this boundary, but we can also take a mix of players in the room. And what will happen then is that we'll get oscillations. We will sort of move around here in this space of possible configurations. So it is possible to describe this type of interactions.
Yeah, but you're talking about a children's game. I'm talking about cancer, which is a very complicated biological scenario. And we don't really see this sort of extinction event. Are there ways to think about this in a sort of more sensible way that's beyond this?
Yeah, I mean, there are also other games that you can model. So if you think that you have that the cells are producing something which influences the growth rate of one another, then we have this thing called the public goods game, which does exactly that. So in this game, instead of having 3 strategies, we only have 2. We have producers and scroungers or free riders. So the way this game is set up is that we have the producer cells. They're producing this public good.
It's interesting that you say that. What do you say it's called, a public good?
A public good, yeah.
So there's actually some evidence maybe in prostate cancer that something like this might actually be happening. Men who have a kind of prostate cancer that's spread and is no longer sensitive to an androgen deprivation therapy, which is when we take away all their natural male hormones, a lot of times their cancers will go away. But some of the cells then learn how to make that chemical themselves, and they're able to keep growing. So maybe that's sort of this idea that you're playing with here.
Yeah, so the way we think about this is that they produce this public good. That comes at a certain cost. We denote that with C, but there's a benefit, right? And this benefit here will fall back onto the producer because it'll increase the growth rate of this cell. But it will also share it in the case it's next to a scrounger cell, so that will also get a benefit. And the way we think about this is via interactions between different types. And this is summarized in a table like this, a payoff matrix here. So if a producer interacts with a producer, then you have a benefit and you subtract the cost, and they both share this because they're both producing. Whereas if a producer interacts with a scrounger or a free rider, what you get is that the producer will only get half the benefit, but it has to pay all the cost because the scrounger is not doing anything except getting the benefit. If a scrounger is interacting with a producer, then it'll get just the benefit. It's not paying any cost. But if 2 scroungers interact, they don't get anything because no one is producing. So what you can do now is that you can look at this from a dynamical point of view and write down equations that describe how the fraction of producer cells change over time. And we have this thing called the replicator equation, which does exactly that. And it tells you that it evolves in this way. So P here is a fraction between 0 and 1, and here we have the difference in payoff between a typical producer cell and a typical scrounger cell. And if we work this out, then we get, with some algebra, we can show that this is what we get, and if the cost is lower than the benefit, which you can expect, then the solution is simple. We actually get a situation where, independent of where we start, independent of the initial fraction of producers, they will always lose out, and everyone will become a scrounger or a free rider.
That's really very interesting, but that's not how it works. So first of all, I like the idea that you've begun with here. I like the idea that there's different types that can interact in this way. And as a matter of fact, I think we've even seen examples of that. But the maths, I mean, I'm going to have to trust you on the algebra there. But this isn't the answer that we see in the clinic or even in our experimental conditions. Can I just show you a little video of what we see? So this again is sort of what we think to be maybe something like your P's and your S's, or your producers and your scroungers, which, by the way, doesn't sound unlike some social situations I've been in. But what we see is, even if you have one winning out, and there is this growth factor being produced and shared, it's never just all one or the other. Because, I mean, look here, like, you didn't mention anything about it in the model you showed. There was just two cells next to one another doing their thing, which maybe I could sort of point to a single scenario where that's happening. But really, we have this large spatial structure that you haven't seemed to consider at all. Is that, I mean, that doesn't really sound like that's feasible in your models. Is that something you can consider?
Yeah, so you can actually extend the model and take space into account. And if we take your picture here, it was of a petri dish, right? So what we can do is that we can take this petri dish and we can sort of discretize it and turn it into this lattice. And in each lattice site here, we can have either a producer cell, which is the greenish square here, or we can have a scrounger or a non-producer, or it can be empty. And the way this works is that the cells will then produce this growth factor, or the public good. It will diffuse and decay, and they will sense it, or they will uptake it, and then they will increase their growth rate accordingly.
So this is really the same sort of dynamic that you wrote the cartoon about?
Yes, exactly, but just in space, yeah.
I see.
And when the cells are then dividing, then what happens is that the offspring is placed right next to the parent. So this is exactly what you showed in your film, right?
Yeah, that's exactly what we see.
And then if this guy decides to divide, then we end up with a new cell there. And then so we can simulate this on a lattice like this by 100 cells. And here we see blue is empty, and red and green are the different cells. And this will show you how the concentration of growth factor changes over time. And if we play this out, then cells are growing, they're dividing, and we see also that the growth factor sort of becomes localized into certain regions where we have lots of producer cells. So the producer cells are now gaining more from the fact that they're next to one another. And what you can show is that, in this case, you actually get coexistence of the different types. So space here really matters.
But you must have also changed something about the game itself, right?
No, it's the fact that you have a spatial situation.
So it's the same?
Yeah.
So if I was able to really distill down what each individual cell was doing, you could then tell me more about how the game changes in space or not.
Yeah, exactly. And actually you can do even more. So what you can do is that you can go to the data here. You showed this, but you can also imagine a patient sample. And you can extract the spatial information that you have here by looking at something known as the pair correlation function. So this function here, which is a function of a distance, basically sums up is the probability of finding a cell type of. So here, in this case, it's a producer and a scrounger separated at a distance r. So that you can measure from the data, but it also comes into the equations that describe the dynamics of this system. So if you want to, for example, look at how the scroungers, how they change over time, then you can write down an equation of this form, where you have a sort of basic growth rate, but then you also have a growth rate which now depends on this pair correlation function and on the public good.
So you can use this sort of formulation to come back toward some idea of the interaction between the cells individually?
Yeah, exactly. And then, of course, it becomes a bit more complicated because you have to describe how these spatial correlations change over time. But this is also a possible approach. So what I'm trying to say here is that we can really infer this game from spatial data that is collected over time.
So, okay, let me just see if I can wrap my head around this. So can I just see if I can recapitulate this cartoon understanding?
Yes, we want to see the,
yeah, can you
have
put
the cartoon
Oh,
again.
yeah, that's it, thanks. I don't remember all the steps in the middle, but what you were suggesting was that you have the two types, which I have seen in both experiments and also in the clinical situation. And that if there was some sort of diffusible factor, which we think there might be, going on between these, you'd have the original scenario where you're going to have only one type winning, but based on these spatial models that you've developed, you can also understand how that would change to be sort of this heterogeneous state that we see. But so now you're suggesting that it's basically to do with this interaction.
Yeah, exactly,
So
yeah.
what would happen, do you think, if we like sort of blocked that interaction?
Yes, we do that, you mean?
Yeah, exactly. If we could turn that off, what would happen in the maths?
I mean, that's going to change the payoff table, and which is going to change the outcome as well. And we'll no longer have this, but we can imagine a situation where we get this instead.
Well, so I could actually see that being of clinical benefit. So this is interesting, because you're suggesting that I don't necessarily have to kill cells. Instead, I could really just interact, or I could just play with the interaction between them, sort of suggesting a different way of targeting a cancer just from the maths. So that really could present a whole new sort of class of biological targets, playing with these interactions.
Yeah.
That's really pretty cool.
Yeah, I think that really maths can help out in a situation like this. But I mean, to me, this is a good idea, but somehow it seems a bit too simple. You're talking about these interactions between the cells, but at the same time you have this population which is actually growing. So things really must be a bit more complicated, right?
Oh yeah, well, trust me, they're complicated. There's thousands of these interactions going on, but really, of course, looking at as few as possible is useful. But actually, this brings to mind, a few years ago, there was a sort of striking paper that was published, I think it was in the early 2000s, where they really suggested that while there's thousands and thousands of possible things a cancer can do, you could really distill these thousands of things down to just a handful. And they were, oh yeah, there it is. It's called the hallmarks of cancer. And really, maybe there's 15 or 20 or 15 or 20,000 different ways to have these growth signals, these producers you discussed. But maybe it's enough to just know that there is a way to interact with that. So do you think we could take this sort of simplified view and come up with a more general model?
Somehow this still seems quite complex to me. So you have all these different traits, right? But if I want to put numbers on these and then sort of put them into a model and see how they interact with, or how the cells behave, this is still going to be quite complicated. Isn't there a way to sort of distill it even further, to make it even simpler? Or
Well, you showed me you're pretty good with one. Let me think. Can I think of a cancer where two things really capture the gist of it? Well, there's a brain cancer called glioblastoma that I treat fairly often. We actually saw some pictures earlier of brains. And in that, there's been a lot of suggestions in the biological literature that you could distill their behavior down to just two things, really.
Okay.
One is the growing a lot, and then the other is sort of this idea of moving. So it's been called a go versus grow hypothesis. And so, but that seems a little bit silly. Do you think?
But yeah, maybe silly, but it still seems hopeful, because if you can sort of distill it down to just these two processes, then maybe we can actually build something, a model that can predict how these things grow.
Yeah, go for it.
So what you can do is that you can take this information. You say that cells they're dividing, right?
Yep.
And then they're moving about, say randomly, because that's what we have good mathematics for that, right?
Sure.
So the cells are moving and they're dividing. So what we can do is that we can set up a model where cells are doing exactly this, and we can simulate it. So this is one example of this. So here you have the cells. Your brain cancer cells here are red. They're wiggling about, doing their random motion, and they're also dividing.
Huh.
So this should capture at least that.
Well, that does look actually like what we see in a dish and what we're imagining is happening at the periphery. But that's like 100 cells or something?
We could scale this up. We could do maybe, if we parallelize this on a cluster, we can do, say, 1 million cells. Would that be good enough?
No. I can't just like 10 to the 10th cells. Can you?
Oh.
Yeah, that's more than 1 million, right?
Yeah.
A lot. So I think this is cute, again, Philip, but I think that it's just not really sensible.
Okay, but actually, luckily enough, we have tools that can help us here. So there are ways here, mathematical tools, for going from this situation of sort of these discrete things, the cells are moving out, up to from this microscopic level up to a macroscopic level, where we're looking at densities of cells instead of single cells. And this was actually done already in the 30s by Fisher, and what you can do is that you can describe the C here is the density or concentration of cancer cells as a function of space and time. And what the random movement contributes here is this thing here, which is a diffusion term. So basically, if the cells were only migrating, they would simply correspond to a diffusion of the concentration out in space. It would just sort of flatten it out. But you're also saying that the cells are dividing, and that contributes with this term here, which is known as a logistic growth term. So this here will tell you that when C is very close to 0, you will have exponential growth. But then, as you reach this, the sort of carrying capacity of the system 1 here, because it's normalized, growth will slow down. Okay.
So how does this relate to the picture you showed me?
Okay, so let me explain. So what you can do here is that you can, given a certain initial state of the system, you can solve this equation numerically, and it will look something like this. So here you have sort of your tumor radius, or the distance from the center of the tumor going out, and here is the sort of normalized density of tumor cells. So in the beginning we have lots of cancer cells. We have a rather small tumor, and we have most of the cancer cells here. And if we solve this equation numerically and move forward in time, what we get is this type of behavior. So the tumor is growing, so we higher density, but it's also advancing here. And what we see is that we get this phenomenon known as a traveling wave. So you see that the shape of this thing is sort of conserved. It's only being shifted in space. And actually what we can do here mathematically is that we can calculate the rate of advance of this wave, and we call this the velocity, and it's actually 2 times the square root of d here, the diffusion coefficient, and rho here, the growth rate.
Again, very nice work. I'm sure this is A+ stuff. But really, when my patients come in to see me, I don't see a traveling wave going across their head. I think I have some pictures of images on the next slide.
Okay, but just let me... So we can also calculate the steepness of the front here, right?
Yeah.
So we have more information than just the velocity, and this we can also relate to the parameters. But I'll let you
I don't really
explain.
see how that's relevant, to be
Okay.
honest. Look, so this is what we see, right?
Yeah.
So this is a typical patient. This is a slightly older image, but this is an MRI, and you can see here that in sort of the bright white on the left, we see the tumor, and around it there's this sort of area of schmutz. We often call that edema or swelling. We think there's actually some tumor cells in there, but really there's a lot of healthy brain. So well, actually, now that you're mentioning it, maybe that is an area of like lower density of cancer. Anyway, well, what I do is I go in, cut the tumor out. You can see it's gone then.
So this black hole is basically
I've done my job.
Okay.
And then, but the problem is that they almost always, and then actually I'll usually use radiation to sort of try to kill any remaining cells that are there. But this cancer in particular is really a bad one, and it almost always comes back. And so you can see on the far right there, that little bright white spot below the black, that's the tumor coming back. But you can see it's pretty clearly not whatever you showed, a wave.
Yeah, but what you were saying here is that this white area here corresponds to tumor cells, right?
Yes.
So the intensity here is somehow proportional to the density of tumor cells?
Yeah. So I'd say that there's probably lots and lots of tumor cells there and fewer there.
Okay, so what if we take like a cross-section through here? Just take a slice here and look at it this way instead. Is this somehow what you'd get? Sort of a density profile like this?
Yeah, actually, that does make some sense. Yeah, so in the middle where it's the densest, so you're saying that would be this peak here.
Yeah, exactly. That would be the middle.
And this might. But in the middle, we do see something called necrosis. So maybe what you're saying there's some death in the middle, and then now that you mention it, that does sort of capture the idea here.
Okay.
But again, I don't really see how it's useful.
Okay. Well, let me explain. So these two images, are they showing different things, or what's going on here?
So here, this is called a T1 post-gadolinium enhanced image. It's quite fancy. We give actually a contrast in the patient's blood, and it collects where the tumor is. So we can really see the density of the tumor itself. And this is a T2 image, which really shows us some different properties of swelling and edema. And so we actually think that does also contain tumor cells. So you can see the brightness where there's liquid and blood, but also there's this sort of fluid around it, which we think corresponds to tumor cells, but in a much less density.
But so you're saying that it measures the different densities here, so you get different thresholds.
Yeah, I think that's not so. Maybe you're suggesting this death threshold here for T2. There's a different one. Yeah, I don't think that's unreasonable.
Okay, but I mean, you said how many pictures like this do you get for a patient? Is it only one, or are there more?
Well, you can get as many as you like. We routinely get 2 before the surgery. We get 1 when they're diagnosed, and then 1 right before to plan the surgery, and then afterwards when they're recurring. So at least 2.
Okay, well, I mean, if you have 2, then you have quite a lot of information, I would say. Because if you imagine that you have these 2, and you take a slice through each, you get 2 images like this. And if we sort of put them on top of each other, we see that this one, which is taken at a later date, in this case, the tumor has actually grown.
That's what they do.
Yeah. But you can actually measure from the image how much is grown, right? And you know the difference in time. So, I mean, that really would allow you to calculate the velocity, right? You would just take the difference, your L here, and divide it by the difference in time. And as I told you before, I mean, we know that the velocity is given by 2 times the square root of d rho, right? So,
but how does that help me? I know you said it's gotten bigger, and I know it's gotten bigger.
Yeah, but you also show these 2 different ways of measuring the tumor, which makes it possible to look at the slope here, right? Because if this detection threshold is further out, then you get a different slope, right?
Yeah.
So here we can from a single image we could estimate the slope and well, simple mathematics allows us to calculate the slope, and here we also can put a number here. So what we have here are 2 unknowns, our rho, the growth rate, and we have our diffusion constant d. But we have 2 equations. We have numbers here on the left-hand sides, right? Well, so we could get for each patient, you can calculate the rho.
That's again, it's pretty neat, and you're making me think how this might be helpful. But I still think it's overly simplified. Is there a way? So again, let's just look at a picture of an image of a patient I've taken care of recently. So here, the brain is again not just one thing going in one direction. I mean, I'm sure you could sort of imagine how it goes in different directions, but you can see it's not the same, right? I mean, some of the directions it's moving very fast, and some it's moving more slowly. And we do have some ideas about how the brain is different in different directions, but I'm not sure how that's going to help me with my planning for surgery or radiation or any of these things. Is there any way you could use that information you just gleaned from the maths to sort of make predictions about how it would happen in real life?
I mean, so I would say... Oh, sorry. First of all, these 2 numbers, even from a simple cross-section like that, calculating, it still gives you information, because if the diffusion constant is very large for a tumor, what happens is that you get this very long tail of tumor cells that are further into the healthy tissue that you hinted at. And maybe that's a way of quantifying how long this tail is, and maybe that can be informative somehow.
Yeah, that would actually help with my radiation planning, because really we think about surgery as taking out the bulk in the middle, and radiation trying to take care of those tails. And so I guess if I knew that it was more diffuse, I could take less out from the surgery and do more with the radiation and preserve more healthy brain. That by itself would be helpful, actually.
But as you said, this is what it typically looks like in some cases, right?
Yeah,
and this is, of course, a lot messy. I wouldn't even know where to put my sort of cross-section here, maybe this way. But actually, we can actually do better, because we now know from repeated measurements on healthy humans what the brain looks like, where you have different types of tissues, where you have different types of fibers. And if the cells are moving at different rates in different locations in the brain, we can make this diffusion constant space-dependent, actually. And we can then not simulate it in a simple 1D, one-dimensional domain that I showed before, where we had this traveling wave, but we can actually do it in an actual brain anatomy in 3 dimensions. Okay, so this will be our domain. We have our initial condition now is like this small lump of tumor cells here, and we can now simulate or solve the equations numerically in this domain where we have this space dependence. And if we do that, then what we see here is that the tumor is growing. The yellow here represent what we can see on the imaging.
Wow, so it's before the tumor is even visible, even if you were to get a scan.
And T2 is that sort of lower threshold, what you can see. You can see that here, the sort of region. And then what you see on T1 is the white bits. So this can really tell you, depending on the location of the tumor, how it will spread and what the invisible part is of the tumor.
And what's really at risk. Wow, that actually starts to be something I could maybe use. And that's all just from those two numbers.
Yeah, and this more fancy technique where you actually take the anatomy into account.
Wow, well, you've changed my mind. That does seem like it could actually be helpful. Thanks.
Yeah, thanks. I mean, I think it's really cool that mathematics can also actually be of help in a situation like this.
Yeah, me too. It makes me think about more things I could be measuring and more ways I could think, and we should probably hang out more often.
Yeah,
Yeah.
thanks.
Yeah.
Thank you, Philip and Jake. That was really entertaining. So I think you should too hang out more. That's what I can agree. So we have time for questions. I know that you actively leave room for discussions here, that you really like that. So please, and that's the same as before, any language will do.
Except silence.
So maybe I can start with one question myself here. That I know that you pretended to be the skeptical medical doctor. Have you ever met any medical doctors being that skeptical as you?
I was underplaying the role. I've mentioned before, my own department chairman refers to my mathematical work as hieroglyphics, and very rare, which is frustrating for your own department chairman. I think the promotion and tenure committee meeting is going to be a bear. But I do think that there's a lot of skepticism in medicine in general, and even in biology, for the utility of mathematics. And I think that we're often codified as only people to analyze existing data and not people to be involved in discussions earlier, which is frustrating. And I think some of the discussion that Philip and I tried to play out here hints at that. There's this richness and wealth of data that we do sit on in the clinical area, but we could never possibly imagine that it could be useful to anyone but ourselves. And I think that the other side of that coin is that we measure a lot of things, but it's often not the exact things that you might want as a mathematician. So I think the earlier these discussions are started, the more quickly we can measure things that are of utility. And the sooner we talk, the more quickly we can see as the medical profession the utility of maths. And so I think it goes really both ways.
So, I mean, even in education, could be some early in the medical education even, or
yeah, I would love that. I'm trying to put mathematical biology into the medical curriculum is not proving easy. There's a lot of, I remember my second year, or maybe first year of medical school, the one equation they ever show you the entirety of medical school, for the most part in the US, is an exponential decay when they're talking about how long drugs stay in the system. And that usually causes at least 3 people to faint. And that's sort of the end of it. And so, but I think maybe some of that's a learned, I'm going to use the word learned helplessness, but I don't want it to be that strong. I think that most people have more acumen for math than they are taught they do. Especially in America, at least, we track early into sort of biology or quantitative. And a lot of times medics come out of the biological side, and there's not as much taught. And I wonder if we could front load more mathematical biology when people before they've given up on maths.
Yes, we have a question over there.
Yes, thank you. That was very interesting. I was wondering, so in your collaboration, you've shown, at least in what you've presented, how you've been able to use existing math to solve biological problems. But have you also come across problems that were too hard for what already exists in mathematics and had to develop new solutions from a mathematical point of view and start new theories?
Yeah, so actually, so when it comes to the spatial public goods that I showed, it actually turned out that, at least when I started looking at this and trying to understand what was going on, the existing tools were not enough. And so I worked quite a lot on developing new ways of analyzing this. And that can actually be, frustrating at times, because you get this strange mix in a paper where you're making a biological statement, but you also have this new mathematical tools that you'd like to highlight. And in the end, it's difficult. It's a difficult balance. So the way it went is that this paper was reviewed, but it was only reviewed by ecologists, and they didn't even look at the math that I was the most proud of, and they rejected it. So. So it's a difficult balance when you do interdisciplinary work.
Yeah, and it's hard to understand. You have to value each individually for their own merits, but the real strength is the working together. But I think that part of the talk that we didn't highlight as much is the fact that I think that often new concepts are brought up that have never been thought of mathematically, and so the opportunity to sort of play in a new sandbox does exist. I think we see that over and over with new sciences.
Question. 5 years from now, what is it going to look like? Healthcare.
I think that's for a different meeting.
I mean, how do you see yourself in 5 years' time treating patients that come to you with a brain cancer?
So can I answer a slightly different question? Can I answer the question, how do I feel that maths will be involved in 5 years?
Yeah.
Or do I feel as though some of these ideas that we're playing with will be adopted to change healthcare? Can I answer that question?
Absolutely.
Cool. I do. 5 years might be too short a time horizon, but I think that we are starting to make significant inroads together. Philip's and my academic father, Star has a group in Florida, Sandy Anderson, who's really pushing. There's a mathematics group in a hospital embedded. I'm trying to do the same, and there's starting to become an awareness of what we do as mathematicians in medicine, as theoreticians in medicine. And I do think that, if you saw my talk yesterday, there's a few clinical trials that are happening. And so it very well could be that in 5 years, these evolutionary principles and the maths underlying them, as methods of prediction at least, will be adopted. And I think, so I think it's up in the air, but and the hopeful side of me says that there'll be a mathematician at every tumor board, and we already have, the CDC already has mathematicians for infectious disease and outbreaks, and I think that if we move from there, we could change the face of it.
Can I also answer?
It's for both of you, yeah?
So I think that there's in general in medicine, or maybe this is maybe too overarching statement, but there's a belief that the latest technology will be what will save the patient. So the more we sequence, the deeper we sequence, the more specific drugs that we can develop, the better we will treat the patients. But what I'm saying in many cases to the people that I collaborate is we can do with simpler things. So maybe we don't have to go and sequence these tumor cells. We can actually do something simpler, which is just to measure how fast they divide and how fast they migrate. So that's what I'm doing in another collaboration with people that work on brain cancers. So I think that looking at it from a different perspective, where the maths is sort of guiding you, I think that can be fruitful. And I think that I'm hoping that will be more prominent in 5 years' time.
Thank you very much. Any other questions about the general healthcare in America, for example? Yes, Charlotte.
So thanks for a very nice talk. The way you cooperate together and you approach the tumor problems, we call often complex systems approach, and you didn't name this, you just said mathematical biology. Maybe you can...
I said complex once,
okay.
at least. So
yeah, okay, but
in my defense, but yeah, of course, when you have all these things that are these entities that are interacting with one another, and you get this emergent behavior, then yeah, of course, this is complex systems, and there's many ways of approaching this. And I mean, I think we all use maths, but come from different disciplines. So you have lots of people from physics as well that do very similar things. So mathematical biology is one name for it, I think, and complex systems or even biophysics is different names, but. Yeah.
Yeah, thank you. We have everything recorded, so we'll check that.
Okay, yeah.
Yes, thank you very much thanks, Jake and Philip.
Thank you.